Okay, so today we'll be talking about the operation research. Uh, uh, this first slide, you can see the title and the reference book. So, reference book that we are using here is written by Hamdi Taha. The title is Operation Research and Introductions. I'm using 8th edition. For those who are experiencing problem, maybe you need to get the other provider, like uh, wired base. Sometimes wireless connection is very, because wireless connection is very dynamic. Sometimes signal is good, sometimes not. I mean, it's a nature. It's like a wind. You cannot expect winds is there all the time. Yeah. So same thing also happens for wireless connections. I don't know. Maybe there is an interference coming to the uh, connections, or is there any congestion in network? So we don't really know about that. Okay, mutual call. What is management sciences or operation research in general? The organization goal is to optimize the use of available resources. So, for example, you are working in a company, in a manufacturing company, and then that manufacturing company is producing goods. Okay, they are producing products. So those product is made from the resources. Yeah, so you need lots of resources, many resources to produce the product. What are the resources? You have raw materials, you have what is it? You have labor, you have utilities, you have many things, yeah, that is used to produce a product. So your goal is, yeah, of course, as an economic creature, we want to get a profit as much as possible with the lowest uh, resources as low as possible. Okay, that's the margins. Okay, so if you are selling something, if you produce something, let's say you're producing 5,000 dollars. Okay, that's the sales. Sales is 5,000, and then the total total cost for producing the goods is, let's say, 3,000. So it means that you have margin of 2,000. Yeah, so that's the margin that you want to increase. So you can achieve it by increasing the profit. Okay, you can sell the stuff, you can sell the goods with higher price if the customer still is wanting to buy, of course. Yeah, if they don't want to buy, and then, well, you have a problem. So one way to increase the margin is increase the sales. Okay, you increase the price of the product, or you are decreasing the resources. Okay. Yeah. So management sciences, or OR, um, in America they said operation research. In Europe or England, in Australia, they said operational research, but it is the same thing. Operation research is a core um, subject on industrial engineering. Yeah. So if you are industrial engineer, you must learn this subject. This subject also learned by, I mean, others. Others program as well. It's like a computer science, because uh, there are some techniques to achieve the optimal solution. Okay, So OR is a discipline to adapt scientific approach for problem solving for decision making. So the purpose for OR is to support management, yeah, because manager's job is to make decision. Yeah, manager is not the person who is doing the operation. No, no. Management is a group of people that is managing the company. Okay, what they do is making decision every day making decision. So it is like um, simple question like how many products do we produce this week? How many products do we need to produce next week? Okay, so those simple questions, right? But how do you know? Can you do it by feeling? Okay, my feeling that next week we have to produce 500. Well, how do you know? Does the market requires that 500 or what? Yeah, how do you get the number? Okay, so if you have three products, if you have two products, product A and product B, you are producing these two products, right? And then mm, how many products? How many product A do you produce? How many product B do you produce? Okay, so those are simple questions, right? But those simple questions is not that easy when you are really get into the real company. You have to do very good observation there, checking the real process, so that you can tell the management that okay, better if you produce X number of product A and Y number of product B. Okay, so here the fundamental of OR is mathematical modeling. So it is a process that translates the requirement or phenomena into mathematical expressions. This one should be is very important. And then here's the process. So we have a problem definition, we have mathematical modeling, and of course after that we do the solution. Okay, so the first step. So again, the first step in OR is, you know, you have to be precise on modeling the problem. Okay, have to be precise with that, otherwise no use. So basic step here: define a problem, model, building model, and then number 3, solve it. So when we give you a task in an exam or homework, yeah, these are the steps that you need to do. Okay, um, yeah. So first step is mathematical model. Okay, uh, so when you finish this one, um, it's already 50% already half of the process. Yeah, so when you get the model right, and then it's already half of the way. Okay, and then the rest is your careful, yeah, your carefulness for doing for solving the problem.
Your
Sorry.
line is now muted. Your line is now unmuted.
Sorry. Okay, so first define the problem. Okay, designing, for example, you want to design or implement new operation. Evaluating ongoing operations, do recommendation, and then identify things or constraints, work management, get feedback, and then build mathematical model. So identify decision variables, which factors are controllable, quantify the objective and constraint. This is also important. So this is also a very good skill for you. So you need to be able to build the model again. Build the model. That's the first step. And then formulation.
Your line is now muted. Your line is now unmuted.
So here you define the objective function. So one general format in OR case is you have an objective function, either it's maximizing or minimizing, and then it is subjected to constraint. Yeah, so for example, you want to maximize. What is maximize? Maximize profit, right? Is there any example for minimizing? Yes, you want to minimize the cost. Okay, but when you are doing maximizing or minimizing, so there are lots of constraints. So here, solving mathematical models, so choose the appropriate solution technique. Either it is optimization or heuristic. So optimization means, so it has to be optimal, and then generate models, and then test is it reasonable or not. So this is one example. Wilson Company produces 3 products. They produces desk, chair, molded steel. It is trying to decide the number of desk, chair, and molded steel. So again, three products. Okay, so D, C, and M. So very um, only on a very simple. I think a very simple company only produces 3 products, D, C, and M. Management question is a question from management is how many desks do we produce? How many chairs do we produce? How many molded steel do we produce? Very simple questions, right? Yeah. And then, so what's your answer? Okay. So you need to get more and more data. Okay. So for this, you can get profit of $50. Chair, $30. Molded steel, $6. What will be this total profit? And then here's the mathematical expression for profit function. So in mathematical, in math, um, you have um, you have to set up a mathematical expressions like set up a model for the given description. Okay, so in this case, if you want to get the total number of profits that we can get is 50D plus 30C plus 6M, right? Okay, so that's the logic. In the real in during your learning of operation research, it is very easy because all the data already given to you. Okay, so you just got information from your lecturer that okay, the company X produces 3 products or 2 products from sorry, 2 products, product A, product B. Okay, if you sell product A and then here's the money you get, is the profit. Product B, this is that amount of money you get, that's the profit of product B. But in the reality, to get the profit of that particular product is not that easy. Okay, for example, if you just buy um, it's like already built-in stuff. Okay, let's say you buy a car already built in. Okay, you already built a car and then you sell again. It's very easy. Yeah, very easy to 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 determine the profit of that of that particular product. Let's say if you have Indofood that produce 1,000 tons of noodle, okay, and then they need tons of flour, flour, yeah. Yeah, it's not that easy. How much money did you get from one pack of noodle? Yeah, because you have to do you know to do lots of calculations, do the operations, and then you can decide, okay, from one pack of noodle, and then this the profit. Okay, okay, for learning, okay, that's fine. All information is already provided. Okay, and then we got another constraint here. Okay, so previously, we have 50D, 30C, 6M, but here it's already you have a constraint that, okay, uh, for the materials point of view, all of those products requires raw steel, okay, raw metal. So we need 3 pounds to manufacture chair, 1/2 pound to produce steel, 7 pound to manufacture a desk. Okay, so what is the function? Okay, it has to be like this. The 7D plus 3C plus 1/2 M. Okay, and then here is another constraint. So unfortunately, at the warehouse, we just only have 2,000 pound of raw steel available. Okay, so and at least 100 desks must be produced to satisfy the commitment. So let's say you already sign a contract from a company, from a customer, that, okay, you promise them you will produce 100 desks. So what will be the constraint looks like? So it's 7D, 3C, 1/2 M, has to be less than 2,000. Why 2,000? Because you only have 2,000 raw material, in this case the steel. And then the D is a minimum of 100. Why 100? Because, yeah, you already promised to your customer that you will produce in 100, but there is a possibility that you will produce more than 100. So that's why D equals or equal D is greater than or equal to 100. So mathematical model for this problem is here. So you type maximize 50D plus 30C plus 6M and subject to 7D, 3C, 1/2 M less than 2,000. That's the first constraint. And D must be greater or equal to 100. That's for your minimum production for dash. Okay, any questions so far? Any questions so far? Okay, next we will start modeling with linear programming and sensitivity analysis. Okay, so when we talk about linear programming is a technique to optimize um, yeah the not only optimize, to find an optimal solution of a problem. Yeah, why is it linear? Because most of the constraints are linear. Okay, you will see that in the graph in the next slide. So linear programming or LP can determine to achieve the best outcome. So best outcome could be maximizing or minimizing. Okay, these are the steps. Okay, same thing. Identify problem, make a model, and then do the work. Okay, another example here. We have Galaxy Industry Production. Okay, so this company, the Galaxy Industry, is producing two models. Okay, so first is Space Ray second zapper. So let's say product X1, X2, or you can say A and B, but resources are limited to, okay, 1200 pound of special plastic, so to produce both toys, and then 40 hours of production time per week. Okay, and then so we have a marketing requirement. Total production cannot exceed 800 dozens. Number of dozen of space ray cannot exceed number of dozen of zappers by more than 450. Technological input: space ray requires 2 pounds plastic and 3 minutes of labor per dozen. Zapper requires 1 pound of plastic and then 4 minutes labor per dozen. Okay, so based on this requirement, okay, you're still observing them and then make the model. We have another constraint here. We have current production plan calls for producing as much as possible, because space ray, if you're selling space ray, you get $8 per dozen. Use resources left over to produce zapper. So space ray is the first priority, okay, because yeah, it's most profitable product. Okay, if you if there are still resources left, and then we can produce zappers. With zapper, we just can only get $5 per dozen. And then the current production is space ray 550 dozens, zapper is 100 dozens, and then the profit is $4,900 per week. Okay. So can you do better than this? That's the question. Okay. So with linear programming, we can provide intelligent solution to this problem. So okay, let's model the case. So decision variable. So yeah, the variable that we can control here is the x1, x2, the total number of space ray produced, and x2 is total number of zappers produced, yeah, in dozen per week. Objective functions: weekly profit, maximize. Okay, linear programming model, max 8x1 plus 5x2 here, subjected to, okay, so 2x1 plus 1x2 less than equal or equal to 1200. This is for plastic. And then so we are subjected to a production time 3x1 4x2 less than 2400, sorry. And then we have total production, so x1 plus x2 was less than or equal to 800, and x1 minus x2, you know, the requirements. Okay, x it has to be less than or equal to 450, and then xj is greater than or equal to 0. J could be 1 or 2. Yeah, so x1 and x2 has to be positive or 0. Yeah, they cannot be negative. Yeah, you know, it's not make doesn't make sense. You know, when people say how many students in the class? Oh, it's -10. What? Yeah, same thing with production. So how many toys do you produce this week? Okay, it's -200. Oh no, it's not. Okay, so it's not correct. So that the last line is important. Okay, not negativity. So it means that we're always playing in the positive integer. Okay. So how do we solve it? Okay, so here slide 11. So when you already achieve this one, this model, it means that you already get 50% of their 15% of your point. Okay, so the first step is set up a model, and after the model we solve it. Okay, so by having a correct model, you only get um, halfway of the solution, and then we solve the problem. Yeah, here we are using the graph approach. Okay, graphical representation of those constraints. So here it is. Okay, so we have 1, 2, 3, 4, 5. So five constraints. First constraint is plastic. Second constraint production time, total production mix, no negativity. So here, okay, um, you draw the lines based on the um, what is it? Uh, Based on the constraint. So each constraint is represented by one line here. Okay, so this is the plastic, and then here's total production. Here is production time. Here is production mix constraint, x1 minus x2 less than equal or 50 or 450. And then the last one here is x2 must be positive, x1 has to be positive. So the area, it leaves the area here. Yeah, we call it feasible area. So inside the feasible area, it's like a diagram. It's like a coordinate. So inside the feasible area is the there are a combination of how many x1 and x2 can you produce. Okay, so this is also it's a good start. Okay, and then uh, get the optimal solution. So we demonstrate the search for optimal solutions. Okay, start from arbitrary profit, let's say profit 2000, and then increase the profit if it is possible. Okay, and then the if you take a closer look, so the area beyond the feasible regions is called infeasible. Okay, if you put here, if you take a coordinate out of the feasible region, okay, you get the number there. Okay, so I have to produce, let's say here x1 is 800, x2 is 800 here, so let's say here if you put in the constraints there will be wrong. Okay, so that's why the area out of the boundary is called infeasible area. The area inside the boundary is called feasible area. And now your problem is you have to find which coordinates uh, can achieve the best. Okay, so here usually the in linear programming like this, the optimal solutions lies on the edge of the uh, of the graph here of the area. So we have 5 points. So this is point A, 0, 0 for you're producing 0 for x1, 600 for x2, and then B, this is 480 and 240, and then we have C here 550, 100. We have D here 450, and then we have E 0.0. Okay, so to determine the value of, so all of the feasible all of the uh, dots in or coordinate inside the feasible regions, all of them are okay, and all of them are satisfied with the all constraint. Okay, but the thing is, which coordinate is the optimal? Yeah. So to determine the x1 and x2, so the two equations of the binding constant must be solved. So here, okay, let's step back. Okay, here. So that we see here. So there are two places, the red one here and then yellow one, where it satisfies two constraints. Yeah. So the first constraint here. So on the red uh, red equations, so it satisfies the plastic constraint and then production time constraint. Yeah, that's the red color here. And then for the yellow color, it satisfies production mix constraint and then the plastic constraint. All right. Okay. So compensation on maximum 8x1 plus 5x2. So we get the coordinate here, x1 and x2, and then you put them into the uh, objective function. So if it's 0 and 0, and then objective function equal to 0. If you use 450 for x1, x2 is 0, you'll get 3600. If 480, 240, you get 5040, and then you check other uh, coordinate as well. So we have A, B, C, D, E. Okay, so you put all of those coordinate into the objective function, and then you will see the you will get uh, the, the the profits. So based on these calculations, we get that 450 comma 240 is the best solution for our problem. Okay, so that's the answer. So you can tell with a confidence to management that, okay, sir, in order to maximize profit, we need to produce 480,000 space ray and then 240 of zappers. Okay, type of visible points. We have interior points, we have boundary points, we have extreme points. So I satisfy all constraint 2 with equality. So here, yeah, we have here several points here. So the point in the middle, for example, 200, 200, so it's called interior point. The points that lies on the edge at the edge of um, an area is called boundary point. And then if there is a boundary point where it's also meet other constraint, is called extreme point. So usually optimal solutions is happening on extreme point. Okay? So if a linear program has an optimal solutions, an extreme point is optimal. Okay, so summary, here it is. You define a problem, set up a model, and then graph constraint to find a feasible point, set objective functions, move objective functions, okay, solve it, the equations, find the coordinates, yeah, and that's it. Another example here, so Ready Mix is the name of company. They produce interior and exterior paints. Paint in English is well, in Indonesia you have a term called paint, melukis dan mengecat, ya. Melukis yaitu melukis, ya, art. Mengecat itu hanya cat saja. but in English both of them are same. So you are painting a wall, okay, also you are painting a picture, yeah, painting, yeah, it's also an art. So here they're producing paints, one for interior, so indoor usage, one for exterior, it's for outdoor usage. So when you have a house, usually you want to paint them, okay, with colors. So this ready mix company, they are the ones that produce the paint. So here is the objective function. Yeah, functions. The functions or row. So it's going to be constraint. So to produce exterior paints, it requires 6M1 and 1M2. To produce interior paints, 4M1, 2M2. Yeah. Profit per ton. So this is gonna be your objective. Yeah. So same. Yeah. Uh, um, same objective from the management. Very simple questions. How many tons should I produce the exteriors? How many tons should I produce the interior? Okay, very simple question for management, but it's not always easy. It's not always easy to answer the questions. Okay, here's the solutions. Okay, x1 is for exterior paint, x2 for interior paint, and then of course the objective is to maximize the profit. So based on the previous data we see here, we get $5,000 uh, from exterior paint, $4,000 for the interior paint. And then the usage of material M1, usage of material M2 per day, daily availability here, availability of M2 is here. Okay, and then restriction. Okay, difference 6x1 plus 4x2 must less than 24, so this is for material M1. x1 plus 2x2 less than or equal to 6 is raw material for M2. The difference between daily demand of interior and exterior should not exceed 1 ton. Okay, so x1 x2 minus x2 minus x1 less than or equal to 1. Maximum daily demand of interior paint is 2 tons. Okay, variable x1 and x2 you cannot assume negative value. So x1 is greater than or equal to 0. x2 is greater than or equal to 0. Yeah. So the last one you have to type. Okay, you have to write the number of the x1 or x2, are they negative or not. Okay, so it's important. If you miss that one, and then most likely your graph will be wrong. Okay, so here's the model. Okay, so z is equal to 5x1, 4x2, and then properties of linear model, proportionally, additivity, certainty. Okay, um, you set up the graph. Here is another example. We have two machines, X and Y. X is designed to produce small bottles, 5 ounce. Y is uh, is designed to produce a bigger bottle, 10 ounce. Okay, so X can produce bigger bottle but loss of efficiency, while 2 can produce a smaller bottle with loss of efficiency. And then here is the constraint, X and Y. Also, okay, X requires 80 per minute, and then if they produce a bigger bottle, it requires 30 per minute, and so as Y. We have X and Y machine that can run up to 8 hours per day for 5 days in a week. profit for smaller bottle is 20 pace. Profit for big bottle is 30 pace. Yeah, so we produce pace as much as possible, seems like. Weekly production of the drink cannot exceed 500,000. Market can utilize 30,000 small bottles and then 8,000 bottles per week, so I think that's maximum. And then the objective of this case is to maximize the profit. Okay, so you get the solution here. Okay, so we have x1 and x2. Yeah, x1 for 5-ounce bottles, x2 for a big bottle, the 10-ounce. Objective is to maximize profits, and then here is constraint. Okay, so x1 divided by 80 plus x2 divided by 30 must be less than 8x 8 times 60 times 5 equals to 2400 minutes. So time constraint for machine Y, x1 plus 40 plus x2 divided by 50 must be less than 2400. Weekly production cannot exceed 500,000 ounce. Okay, and then market demands, x1 higher than 30,000, x2 is 800,000. Okay, so here is another example. We have two types of product, okay, A and B. Profit is for, okay, RS here means rupee. Yeah, rupee. Rupee is the name of the currency in a country in the world. That is India. So in India they call it rupee. In Indonesia we call it rupiah. Yeah. Okay. Next question is, if they say it is rupee, and then why do they put RS there? So for us, because we are using rupiah, we put RP. Yeah. But they are using rupee without S. So in my thinking, it looks like it's a plural form of plural form of that one. So rupees, like rupees. So it means that this is a plural, not singular. Yeah. So RS4 type A, RS5 for type B. So those are the profits. So I think this one is the objective is to maximize the profit. So product A. So product A is requires 2 minutes. Product Y 3 minutes. Product B requires on machine X is 2 minutes, and then product Y is 2 minutes. Hello, somebody that's stuck. What do you mean stuck? Anybody is having same problem? Okay, so that means problem with your connection. Okay, yeah, that's fine. Yeah, so only problem with her. Oh yeah, so I believe that there is a URL where you can check your own system, whether your system meets the minimum requirements or not. Okay, machine Y available for that. Formulate the problem as linear programming, and then here it is. Okay, we have here's the solutions, and then here's the objective. Okay, so I would expect you to write this kind of thing on your exam. Okay, so you define the decision parameters. Okay, in this case is x1 and x2, and then you put the objective. Okay, what's the objective? So you want to maximize. You type here maximize profit z equals to 4x1 plus 5x2, and then after that you type constraint. So those this template, you can call it template, yes, is needed to solve the answer. Yeah, so I would expect you in the exam to write when you I would expect you to write with this kind of template. Okay, complete linear models here, subject to here. Okay, based on those constraints, you draw graphical linear programming solutions. Okay, for ready mix model, so in the first example, here's the example of the modeling. Okay, and then change all equals equation to equality signs to draw the lines. Okay, and then plot the graph. Okay, here's you get. Okay, so for ready mix, the company that produce painting, exterior and interior paint, we have 1 2 3 4 5 6 points or coordinates where you can apply to the objective function. Okay, so doing that, and then you'll get the answer. Okay, another example is here. Oh, sorry, still the same. Okay, and then yeah, one important characteristic, as I said before, usually the optimal solutions, but not always. Yeah, usually the optimal solution for this is located on the extreme point. So it's the point where two or more uh, um, constraint met. Okay, so we have, for example, optimum on point C here. Okay, so it satisfies uh, here DC and then CB. Okay, CB is a line of one constraint. DC is also a line that is made from a constraint. So both constraints meet at C, yeah, point C, and then you get the point C, and then yeah, get check whether it is optimal or not. Okay, so based on our testing here, we get that at point C, the Z is 21, so which is the optimal solution. Okay, so previously we always talk about the maximizing. Is there any minimizing? Yes. Usually we want to minimize cost. This is one example. We have two plants, Combator and Chennai. We got cost per day on each location. So if we produce in Combator, the cost per day is 600. If we produce in Chennai, it's cheaper, it's 400. So same questions. How much do you? How many days is plans to be run in April? So in order to minimize the production cost, yeah. Okay, so uh, you get the constraints on this slide here. Okay, based on those informations, you set up the modeling. So same template. Okay, so first solution is first define the decision variables x1 and x2. Define the objective, is it maximize or minimize? Okay, and then a constraint, and then draw a feasible space here. Okay, draw the lines, and then yeah, that's it. You pick each of the extreme point. Okay, and then based on that you can get the optimal solutions. So optimal solution can be maximum profit or minimizing, uh, usually minimizing costs. Okay, so if I said optimal solution is not always associated with a profit. Okay, next is sensitivity analysis. So you get so currently you already have the 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 coordinate. Okay, so you have to produce x number of x1. You have, and then you're also able to get the number of y, yeah, y product. So the next question is, can we adjust the constraint? Yeah, so that's the purpose of sensitivity analysis. So so it means that we need to put coefficients there. So if you have a functions, usually functions, function is mathematics. So you have y equals to x, for example. So if the function is y equals to x, and then how it looks like, it's a very straight line with 45-degree um, um, uh, 45 degree of deviation from the axis. Okay, yeah, so y equals to x. So what happens if y equals to x plus 1? So it means that the lines will be shifted to the right. Okay, what happens if you have functions y equals to x minus 1? So it means that the lines will be shifted to the left. Okay, next, what happens if you put a coefficient on that variable? So it's gonna be y equals to cx. Okay, so I repeat, in the beginning you have y equals to x. Okay, so it's gonna be a straight line with 45 degree. If you have x and y axis, so it's gonna be 45 degree from x. Yeah, from x axis. So that's if you have y equals to x. What happens if you have y equals to cx? And then we need to play what is c. So if the c is 1, that's gonna be y equals to 1x. Okay, so it's gonna be the same 45-degree line. So what happens if the c is called coefficients, is less than 1? Okay, so y equals to 1.5x. Understand? So it means that the degree will be lower than 45 degrees. Understand? So what happens if the c, the coefficients is more than 1? So let's say y equals to let's say 3x. Okay, so the declinations, okay, it's gonna be more steep. Yeah, so the degrees will be higher than 45 degrees. So the range of optimality here is determined by the coefficient. Okay, so the proposed for analysis is like this on this slide. So how far can we adjust the constraint here? So let's say we have one line here. Okay, we get the optimal solution at this point. So how far this constraint and these constraints can be adjusted? Okay, yeah, that's determined the coefficient. Okay, so you'll see here maximum 3.75 x1 plus 5 x2, and then here is maximum of 10 x1 plus 5 x2. So that is the range between 10 and 3.75. So as long as the constraint is between that, you're just fine. And then still you still give optimal solution. Okay, so other name for the constraint for the coefficient is called slope. Okay, so how steep is the line? Ngerti steep ya? S-T-E-E-P. So the binding constraint is here. So the slope will be minus 2 per 1 or minus 3 per 4. 3/4 or 2 ones, minus 2, yeah. To find the range optimality of space ray and coefficient per dozen of Zapper is C2 equals to 5, and then the slope of the objective function line can be expressed as minus C 1/5. So this is the optimality range for C1, yeah, found by solving the function of C1 here. Okay. Range optimality of Zapper, coefficient per dozen space ray is C1 equals to 8, and then the slope for the objective function would be divided by A divided by C2. Okay, so range optimality is here, and then done. We also have one software called WinQSB. It is a Windows software. It's 32 bits. You cannot run it on your 64. It has to be 32 bits, so you have to install an emulation software like a VirtualBox or VMware. So WinQSB requires input data from you. So this is how WinQSB looks like. Actually, if you are still studying here in a university in semester 3 or 4, I'm not sure, there will be a subject name operation research, and then so you have to take it in 2 semester. So there will be more deeper discussion regarding to operation research in the subject. So WinQSB is the software for operation research. You can do many things there. Okay, so it's got linear programming, see here, non-linear programming, goal programming, forecasting, facility allocation and layout. Yeah, so they can do many things. So what you can do here, you can click the linear and then integer programming, type the problem titles, number of decision variables, number of constraints, and then put the functions there. Okay, what is the maximized function of x1 or x2, and then set up the constraints. Okay, and then modify the constraint name. Is it plastic, production time, total, mix, and then solve the problem, and then you get it. Optimal solution is achieved. Okay, then here's the result. Done, and then finish. Okay, any questions for this one? So you can download WinQSB from the internet. I think it's available there, but I'm not sure from which website it's can it be can you download it, or maybe you can ask your senior or the assistants. All right, any questions? Any questions? We will release the so I think today or tomorrow, yeah, tomorrow so tomorrow is the deadline for the submission, yeah. So today we'll set up the uh, we'll set up the what is it set up the, 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 the activity so that you can upload it by yourself. Any questions? Are there any questions? So we found a homework in Moodle about LCN, yeah, but it was due to in October. Yeah, that's fine. Yeah. So Bu LCN, Bu Lucy. It was the an assignments in the class, yeah. So you don't have to worry about that. Yeah, that's fine. That's fine. Yeah. So it is for Bu Lucy. Okay, so Bu Lucy will will give you the numbers later on. Okay, so you don't need to worry about that. So what you need to worry is your final project. Make sure it's you submit the assignments beforehand. Yeah, I see here. Okay, some students who are not you know were not telling the truth. Okay, and for example, is the format same as industrial game? Well, could be same or not. So you should see the instruction. What else? Um, what should I say? Yeah, about the submission. Okay, so this is very important. We found that a student saying that I cannot submit because the Moodle is error. And then we ask, okay, where's the screenshot? The students cannot provide it. Yeah, so we cannot consider that um, as as a complaint. Yeah, so because it's difficult for us to say what happened if the student is not telling the truth. Okay, so if you want to if you have a problem with Moodle, and then take a screenshot for that, and then we'll follow up for you.